Okay, if you didn't watch the live lecture, here's the information you missed and what you need to know. I would grab your notes. We already covered what a differential equation is and showed a very simple example of it. And I'll walk you through the boat problem. These are the only two types of problems that you'll see for differential equations on the AP test. And so here's the scenario. This is the same one that's in your reading, but this could be a block going across the surface, could be a lot of different applications. Boat's traveling along and the motor dies, causing it to coast to a stop. The drag of the boat on the water is dependent on velocity. And they want to determine an equation for velocity. So what's velocity as a function of time? You plug in a time and I will tell you the velocity. If the force of drag is equal to negative b times the velocity. So as velocity is high, I have a large force. As velocity decreases, this force vector gets smaller and smaller and smaller. How do we solve this? Well, we have to set up a differential equation to solve it. Before we do that, I just want to make one note what this negative means. The negative means that your velocity and force are in different directions. I'll just say oppose each other. And we call that a retarding force, a force that slows down. Friction is a retarding force. This is a force that slows you down, but it changes in magnitude based on how fast you're going. And that could be how much water is pushing around it, how deep the boat is, and things like that. B would just be a constant, depending on the shape of the boat, the water, and things like that, just a constant. So how do we solve this? The first step for solving any of these force problems where force is a function of velocity, you want to use Newton's second law. And I would write Newton's second law not as F equals mass times acceleration, but as acceleration equals your net force divided by your mass. And that allows you to have your variables on the left side all at once. And I'll show you what that means here. So our net force, we only care about the x direction here. We'll call this the positive x direction, and this is the negative x direction. And that means my force, my net force in the x direction is just going to be this force, so negative b times v. So my net force, A, equals net force, negative b times v, over my mass. That's your first step. And then we want to turn this into a differential equation. So we're going to take A, no calculus here. We just represent A as the derivative of velocity with respect to time. That's equal to negative b times v over my mass. Now I have a differential equation. I have a variable v that's changing. My velocity gets smaller and smaller over time as the boat slows down. These are just constants b and m, but I have my derivative of v and my derivative of t. So I need to get these v's on the same side and the t out of the denominator on the right side. So I'll divide both sides by v, dv over v equals, multiplied by dt on both sides, negative b over m times dt, and I've separated my variables. Once your variables are separated, you can integrate both sides. And if I integrate the left side, the integral of dv over v is the natural log of v. The derivative of the natural log of v is dv over v, plus a constant. We're doing an indefinite integral. There's no limits here to integration. Equals, I'm integrating this with respect to t. There is no t here, so this is just a constant. What's the integral of a constant with respect to time? Well, it's just going to be negative b over m, my constant, times time, plus c. We'll call this c1 and c2. If I have constants on both sides, I can combine those to just be one constant. So you can subtract c1 from both sides. That would give me one new constant here. I'll just call it c. And c1 minus c1 is 0. So I get natural log of v equals negative b over m times t plus c. And what do I want to solve for? I want to solve for this velocity. Velocity is a function of time. So this is my function. And what's the function of time equal to? Well, it's equal to whatever the solution to this equation is, solving for v. There's my t on that side. So how do I get rid of the natural log here? Raise both sides to the e. So e to the natural log of v is just v. And I'd end up with e to the negative b over m times t on this side, plus a constant c. And that's my function of velocity with respect to time. We're not done here because there's a constant c. We need to figure out what c is. Well, to do that, you need to know some initial, final, or some other point throughout its travel, the velocity of it. The only thing that we know is at the beginning of this, that velocity time of 0, v of 0, velocity is v0, my initial velocity. And so we're going to use those circumstances to calculate what c is here. And that's v0 is equal to v sub 0. And v0 is equal to e raised to the negative b over m times t, and t is 0, plus c. Well, that's going to be v0 is equal to e to the negative b over m times 0 times e to the c. That's how we break apart these terms. Well, this is just going to be 1. Anything to the 0 power is 1. And so we get v0 is equal to e to the c, which is just a constant c. So we get c is equal to v0. You might not like how I did that there. Let's break it across up over here. V equals e to the negative b over m times t times e to the c. Let's make this a constant, and you might make more sense of this. Let's just call this c. E to a constant is just going to be a constant. So v equals c times e to the negative b over m times t. And this might make more sense to you if you plug in v0 here. V of 0 equals v0, which equals c times e to the negative b over m times 0. Plug in 0 for your time. This is going to be 1. And now it's a lot easier to see what happens here. Initial velocity is equal to your c, which is in front of it. And you get this. V of t is v0 times e to the negative b over m times t. And there's my velocity function. What does that mean? This is a negative exponential. So this is exponential decay. Starting at your initial velocity, e to the negative power is going to be 1 over e. So this will be a fraction here. As time increases, the fraction gets larger and larger and larger. Denominator, which means it's a smaller portion of my initial velocity. It's going to get lower and lower velocity. And if you actually graph that, it looks like this. The slowing down boat, we'd have an initial velocity. This would be v0, and it slowly decreases, decreases, decreases. And that makes sense because my force would be greatest here with my highest velocity, so it'd have the greatest deceleration, greatest slope of my line, and it'd have the least deceleration at the end when I have the smallest velocity, and this would just decrease over time. It'd be asymptotic to 0. So this won't ever reach 0. It'll just get really, really close. The limit as t goes to infinity for this equation is 0, but it won't reach 0. And you might say that doesn't make sense because if you've ever experienced this, if a boat cuts its motor, it does reach 0. It comes to stop. The reason why our function doesn't go to 0, but in reality the boat actually does stop, is because this estimate right here, my drag force equation, is an estimate that's based on velocity. It works good for high velocities. But as you get to extremely small velocities, this equation would say that the velocity would get really, really close to 0, which means my force would get close to 0. And at that point, it's not necessarily the frictional force of the water particles going around the boat. You start to get some of the attractive forces, and the velocity would just kind of, or the force would kind of flatline at a minimum value. It won't go down to 0. So it would stop our boat. So it's not a perfect relationship, but it works for everything that we're looking at for most times. Okay. How would we get the distance traveled by the boat? Well, we go back to this page and we think of our relationship between velocity and our x position function. Well, position is equal to the integral of velocity with respect to time. And I can just integrate this equation that we just got here, v0 e to the negative b over m times t with respect to t, and I'll get my position function over time. And position, we can do this, is equal to v, my constant stays out there, e to the negative b over m times t. You could use substitution here if you wanted to. What do we get here? Negative m over b times all this plus c, the constant. We should evaluate what our constant c is here again. And what do we know? At x equals 0, we usually define it as 0 meters. So let's use that. x equals 0, b 0 meters equals negative m over b v0 e to the negative b over m times t plus c, and our t is 0. So if you plug in 0 here, e to the 0 power, this part of it goes to 1, and 1 times negative m over b times v0 is just negative m over b v0 plus c equals 0. And it's pretty easy to see here, c is equal to a positive m over b v0. And that can be plugged back into our expression, and we get x of t equals negative m over b v0 e to the negative b over m times t. That's this right here, plus our c, m over b v0. And that would be your function of x. You could substitute this out if you wanted to, but you wouldn't have to. And the function would look like this. You have an initial change in position that's really great. We'd be going the fastest, and the boat's going farther and farther away. We almost reached 20 meters away from where we started, and then it gets smaller and smaller changes in position as the velocity decreases over time, and it flatlines, and that would be our boat is at rest. Okay. So hopefully that helps you see how we'd evaluate this particular problem. That's it for that type. I'll show you your last type in a separate video.